Hi, everybody, and welcome back to Environmental Science on this wonderful weekend. Hopefully, if you're here, then you are winning the time change and you are on time and you know what's up. I always think it's amazing to think about how did the time change work before we all had smartphones to tell us what time it was all the time. I feel like a lot of people were probably late for work and school because of that. So let's go ahead and open up the chat here. Good to see everybody back. All right, so I'm going to go ahead and share my slides and we will just jump into today. As always, please keep talking in the chat. Let me know if you have any questions or if there's anything that you want me or our wonderful TA to cover as we're going along. And again, please help each other. Don't be shy about answering each other's questions. Let's see, all right. So today we're going to go over Unit 4 for Environmental Science, Earth Systems and Resources. As always, if you don't want your real name to show, please change it. And please follow us on all of our social media platforms to find out the latest on what we are doing and different support methods that we offer to help you get ready for this exam. This is what's coming up. We, believe it or not, are already, next time we're going to be going over Unit 5, which seems crazy because I feel like we just started, but we're already a good chunk through all of the curriculum, be about halfway once we're done today. So that's a lot. You're doing awesome, and we are getting through it. And then I noticed last time someone asked, like, when are we going to do free response help? And so how the course is structured is we're just going to run through all of the content first. And then once we do that, then we're going to do free response for 3 weeks. So we will do a lot of free response practice, but we're just going to do it kind of all at the end. And the reason why that makes more sense to do it that way is because none of the free response questions are going to be on just one topic. They're always going to be a mix of a bunch of different topics. So for like a real authentic free response practice, you need to be able to already have all of the content down. And I hear some people on the chat saying they can't hear me. So let me just make sure before I keep going that people can hear me. Put a smiley face in that chat if you can hear me, okay? Otherwise, I will troubleshoot what is going on. Okay, seems good. Seems like, okay, awesome. Seems like people can't hear me. What were we talking about? Yeah, anyways, so you just need to have all the content down before you do free response because the questions are often going to be like asking, you know, how does one thing affect something else? And you really couldn't answer like an authentic free response question without covering all of the content already. So that's why we structured it like that. And as always, trivia is the day after our CRAMs. And if you have not yet joined that, please do. It's a fun way for you to practice the information that we have gone over. And those are like content specific for each unit. So then one tomorrow is just going to go over what we covered today. So you'll be able to practice how much did you pick up on from our CRAM today. And then that brings us to what we're going to go over today. We already did our intro. So we today are going to be talking about plate tectonics, soil formation and erosion, soil composition and properties, Earth's atmosphere, solar radiation and Earth seasons, Earth's geography and climate, El Niño and La Niña, and within that, global wind patterns. And I do have to say this unit is probably, as far as how they're structured, like in units, this one I feel like is the toughest to like stay motivated for. Definitely not like the toughest as far as content, but you know, kind of my like saying as we go through things for environmental science is, what was the thing naturally? How did humans mess it up? And then how did messing it up like in turn affect us? And this unit is really just like the basics. It's like talking about sort of like processes on Earth, and not really jumping into like how humans have affected them. That kind of comes separately at Unit 9. And I just personally believe it's hard to like understand why you need to learn all these things other than just the sake of memorizing stuff without putting it into context. So I don't love that, but we will jump into it as much as we can, and I'm going to try and give you context as far as like why these things matter as to humans and how we've kind of messed it up as well. Even though as far as the way the course is really structured, this is it's not really in there for this time. All right, plate tectonics. So this you have probably been hearing about in your science classes since like 5th grade or so. Plate tectonics is like the theory of plate tectonics is saying that Earth has layers, and the topmost layer, the lithosphere, is broken into plates that move around. Where those plates touch are called plate boundaries, and how they move causes different geologic features. So in our little map there, you can see the little arrows, how they're moving. Those plates move around. There's 15 major plates. Don't need to memorize that. That's just a fun fact. And how they interact with each other really dictates what geological features are going to appear in that, you know, given area. So whether or not they're crashing into each other or pulling apart from each other or sliding past each other. And so we can kind of predict what's going to happen based on that. Here, let me make the picture a little bit bigger so that you can see where everything is and see those little arrows. And we're going to come back to this. So let's just get a little bit more definitions in, and then we'll come back to this picture. Convergent plate boundary means to come together. To converge would be to come together. Anytime that two plate boundaries are coming together, they're kind of smashing a bunch of material into each other, and that forms a mountain. And then anytime that that's happening, you're going to have earthquakes and volcanoes as well, or can have earthquakes and volcanoes. Divergent, to diverge means to go apart from, to move apart. And where that's happening, you are likely to have seafloor spreading, very deep valleys, earthquakes and volcanoes as well. And then transform or strike slip faults means to move past each other. And in those places, typically you're going to have more earthquakes. Understanding the location and type of a fault, we can predict the locations of potential earthquakes and volcanoes, as well as the resulting impact they can have to human health. So let's jump back here to our picture. So looking at how all these different plates are moving, you can see where some occur and those different relationships, that's going to cause different types of things to happen as far as we're going to have volcanoes there, or if you're going to have major earthquakes. And one thing to note that I always think is really fascinating, especially for if any of you are from or currently live in California, look at how big the North American plate is. So that's that purple one on top. That's like obviously the entirety of like North America. It's huge, right? It's massive. And then also look how big that Pacific plate is. And that's that yellow one. So these two huge major plates, like large, significant chunks of the Earth. And then if you like zoom your eyes in to where California would be, Southern California and like at the Baja of Mexico is like right on the Pacific plate, where the rest of California and the rest of the US is on the North American plate. So it's nuts to think about that, like just this teeny tiny sliver of land of Southern California, basically like Southern California up into like San Francisco, is on an entire different chunk of the Earth. it's kind of crazy to think about. So like that is just a teeny tiny bit of land overall for how big that plate is, but we're living on where those two plates crash into each other. For any of you living in California, and you can actually see the fault. Like you can see exactly where those two plates come together. And where I used to live in Southern California in a little town called Wrightwood, and the fault went right through the middle of the town. And you could even find rocks that are called fault mirrors, where it was a rock that was like ground up against other rocks as the plates moved together, and it's like all shiny on one side because it got really hot during the earthquake. So absolutely crazy that occurs in such a small little place like that. And then how that really matters to us, like why do we care what the faults look like, is it impacts like our lives, right? Like if you lived in Wrightwood, you would care about the earthquakes because you live right on the fault line. And same thing, like a lot of times the different types of faults cause different things like a tsunami. And a fault that's moving past each other is not going to have great amounts of lift. So that's why you don't really hear about tsunamis hitting the coast of California, because that fault is moving past each other. It's not jumping up and down. Jumping up and down is a loose term, but it is not subducting underneath the ground and causing any uplift or anything like that every time it slips. Whereas if you look over towards Japan, those two plates are coming together. And so when it does have a slip, one plate is going to slip underneath the other, causing a large movement vertically. And if you have a lot of water on top of that, it's like if you're putting the sheets on your bed, and you like lift them up in the air really big, you can make this giant wave in the sheets. Basically, that's what happens to the ocean. And that's a tsunami. So it is important for us to know these things so that we can be ready and plan ahead, knowing what could happen as a result of these different earthquakes. All right, so moving to soil formation and erosion. Over time, soil is created by the process of erosion and deposition, as well as the slow incorporation of biotic matter. So again, biotic means anything that is from a living organism. Abiotic would be anything that was not from a living organism. So abiotic things are like air and rocks and minerals, and biotic would be little pieces of leaves or decomposed pieces of animals or anything like that, even if it's down to just like very small units of an animal or a unit of a leaf, very tiny bits. So that is what makes up soil. So soil is not considered biotic or abiotic. It's a mixture of the two. And it does take a while to form. You remember kind of what we were talking about with primary and secondary succession, and the formation of soil happens over a very, very long time as plants live and then die and their bodies decompose, and we need the soil, the rocks and minerals as well to be broken from large pieces of bedrock into tiny little rocks. So soil formation does take a long time in order to happen. And I know the slide at first is kind of like overwhelming. There's a lot going on there, but we'll kind of break it down here. So on the left is a drawing of soil horizons. So if you're looking out into the horizon, you're looking at like layers of the atmosphere, layers of a sunset or something. So when we look at the horizons of soil, we're looking at the layers of soil. And in this little drawing, and then on the right side, that's just a picture of like an actual. I know sometimes we always just look at like diagrams of stuff in science. So that's like an actual picture of soil horizons that you would see if you were a geologist or something out looking at soil. And then we can break down these horizons. I would hope there's not a memorization type question on the test where they ask you like, what's in the A horizon? But there might be. So it is worth it to take the time to kind of memorize which each of these letters of horizons stand for and what they mean. But yeah, I would hope they wouldn't ask you that because that's just kind of like a recall question, but they might. So again, the O horizon, O stands for like organic, because that's going to be just like leaf layers on top, dead plants or like plants that have recently fallen over. And that's going to be like the very top layer. And then A and B are going to be topsoil and subsoil. So that's kind of easy to remember. A is on top of B, or before B, so topsoil and then subsoil. C horizon is going to be weathered bedrock. So I don't really have a mnemonic device for the C. I don't know why they chose to put C. And then R horizon is going to be, just think of R for rock, and that's going to be bedrock or solid rock that hasn't been broken up yet. So like large pieces of rock at the bottom. And then like as far as when you're looking at soil health and like where is a place that has healthy soil or is good for plant growth overall. And when we're talking about like primary or secondary succession, looking at how much soil is in an area kind of tells us how long that ecosystem has been there and kind of been unchanged and exposed to different weathering events. You're going to see different depths of soil. So places that are like brand new, where you just had like a volcanic eruption, it's just going to be bedrock. There's going to be none of that soil on top of it. But a place that has been around for a very, very long time and experienced a lot of erosion events is going to have a large depth of soil. And like, for example, different places where this occurs, again, the volcano would be just the soil, but a place with like a lot of soil, anywhere kind of on the Mississippi Valley. So any of the like very interior states in the US are going to have, in general, very thick soil because it is very good for growing plants there, so that there has been a lot of opportunities for those plants to grow and die, as well as that area was covered by glaciers in the last ice age, and those glaciers receded, allowing for there to be a lot of erosion events and deposition of different materials. So anyway, so places like Iowa are going to have pretty thick soil layers. And then just some more definitions here, going like, what's the difference between weathering and erosion? That might be a question that you'll see on the test. Weathering is rocks being broken down, and erosion is the removal of matter. So weathering is rocks being broken down, and that is, happens from rain and wind, and sometimes animals can break down rocks. A lot of times trees or other plants can break down rocks with their roots. And then erosion is when it does rain the next time, that soil moves from one place to another. And how humans have affected this process is we've dramatically increased the geologic timescale for erosion with large-scale farming. So from that picture, let's go back. This picture here is of a farm that has recently been tilled. Tilling is when you pull a device behind a tractor that kind of mixes up the land. And so it creates these divots that are really good for planting different plants, and they help channel water so that water can kind of like flow through the land and access all the plants. Tilling also makes the soil really good for the plants because it's aerated and loose. It's easy for their roots to go through it and take hold. So that is why we till land. But if you can imagine this field right here, like if you look at that picture, that soil, it looks very soft. You can imagine you could like grab it and it would be like picking up some sand or something very light. If there's a massive storm that rolled through here with like heavy wind and water, all of that soil is just going to run away in a giant muddy mess, right? So if everyone over thousands of miles are tilling the land like this, and then there's massive storms all the time, the soil is going to go away, and then there just won't be soil anymore. Eventually it'll just go back down to that bedrock. So it is a very valuable resource, and we have to protect it. You can't just like let it wash away into the Mississippi and eventually wash away into the ocean, because it's just gone. And it takes a really long time for it to come back. So the way that we've kind of said we can get around that is no-till farming. So that picture on the bottom right there, I believe those are soybeans growing. And then if you look at the soil in between them, it has like sticks and stuff because the plants that were going there previously, they didn't till it. So plants died and like fell over or were cut down, like trimmed. And then they just planted the next crops on top of them. And then now they're growing. So now if it rained here, that those leaves and stuff would protect the soil so it wouldn't wash away. So that's no-till farming. And it's actually mandated in a lot of different states in the US or different places where they say you can't till the land anymore, because if everyone keeps doing this, we're not gonna have any soil, and then we're not gonna be able to make food to feed people, and it's going to be bad. You'll have like a collapse of the farming industry. So they have mandated that. But I know a lot of farmers aren't a fan of no-till farming. It's hard to plant your next crop when there's a bunch of dead crops on the land. It's hard to get the seeds into the ground. As well, it's hard to get fertilizer to the roots of your plants. It's hard to get water to the roots of your plants. Sometimes the water just rushes away now. And sometimes the plants don't like it. The plants don't grow up as well. And, in addition, when you have those decaying plant matter on top, they're not in the soil. So that nutrients is not incorporated in the soil. It's just sitting kind of idle on top of the soil. So there's pros and cons to both of these. And, that's something that like scientists and farmers are working together on, to try and come up with a solution that works well for everybody, that can still grow lots of food and support people and farmers, and is going to be sustainable. All right, and I think we do have a poll question on this one. Is soil considered renewable or non-renewable? This is a tricky question. All right, take one more second to go ahead and vote on that one. I'll go ahead and publish our results here. Soil is considered renewable. And that kind of brings us to, what does renewable and non-renewable mean? Technically, it means, is it considered renewable within our lifetime? Can more of it be built up within like a person's lifetime? And if it can be, then that is considered like a renewable resource. If it takes longer than our lifetimes to bring it back, then it is going to be non-renewable. So soil is, it's going to be considered a renewable resource. It does take a long time to come back, but it can come back within our lifetimes and replenish in the areas that we need it if it is protected. That one. All right, so let's just keep going on here about soil. So soil composition and properties. The specific composition of the soil impacts its potential to support primary production, based on water retention and nutrients available. So in our picture here, I have an outline of the watershed of the Mississippi River, and it is absolutely massive, the amount of area that drains into that one river. And again, that's what a watershed is. A watershed is anywhere that gets rainfall that drains into one river. So you can kind of go from like a big river and you go backwards, like where does any rainfall that happens here, drain into that same river? And that's all considered the watershed of that one river. And the reason we kind of want to know that, like, where is the water coming from for this river, is because we can track like, this river seems to have some sort of crazy pollutant in it. Do we just look, a mile out? the whole way? Or for the Mississippi River, do we need to look all the way over there in Bozeman, Montana, because that's where it starts, which is crazy. It's super far away. And actually, the headwaters of the Missouri River are really close to where I live here in Bozeman, Montana. So if I were to throw a bunch of pollutants in the water, it is going to affect a lot of people down the road. So kind of a sidetrack there, but that's why we look at that whole huge area as far as where water comes from. And that impacts soil as well, because that is how water transports soil in the process of erosion, and then deposition is where it gets put down. So that is how a ton of nutrients has moved from Montana and Wyoming, and now that kind of basin of the river is very nutrient rich, and that's why we grow so much crops in that area. All right, so soils with large particles allow water to pass through and to be lost. So soils with large particles allow water to pass through and to be lost. Soils with small particles and a lot of organic matter have a high cation exchange capacity. Don't be afraid by that. You don't have to remember that, but the reason I put it in there is because it helps you kind of understand why this is important. The cation exchange capacity is the process by which plants absorb nutrients with their roots. So if a soil has really small particles and a lot of organic matter, they are going to be able to send those nutrients into plants very well. If soil has large particles, like let's say in a desert with a lot of sand, those plants are going to have a really hard time absorbing nutrients. Even if the nutrients are there, they're going to have a difficult time absorbing them. So it's a lot more difficult for plants to grow there. But places that have really fine soil are going to be able to grow a lot more plants. And for humans, why that's important to us is being able to test the soil allows humans to make smart choices about the development of natural spaces. And if we can make, 2 farms that are the exact same size, but if we make one in a place that's going to grow twice as much food, we don't need to impact the same amount of land. You're going to impact a smaller amount of land with a higher result by being able to choose smart places to grow our food. And then this diagram here, this is kind of looking at the different compositions of soil based on clay, silt, and sand percentages. So you can see like on the bottom there, all the way to the right is going to be 0% sand. And then all the way to the left would be 100% sand. So soil is going to be composed of sand, clay, and silt. And depending on the numbers, you can then identify a different name for it and then look into its potential to its cation exchange capacity based on the size of the particles. So as far as this diagram, it might appear on the exam. So it's good to understand how to use it and to be able to locate these different names on here by looking at the different percentages of sand, clay, and silt. So the test might give you a question that says something like, if something contains 80% sand and say 20% clay, where would it exist? And that would be in that sandy loam area. So being able to identify the different composition there. All right, so let's just keep moving right along and talk about Earth's atmosphere. Earth's atmosphere is broken into distinct layers based on composition and temperature. Humans have impacted these different layers in different ways. And the first thing we need to do is just kind of memorize the different layers, but you don't really have to memorize them all. There's only those 2 bold ones that are really important as far as what you need to know for environmental science. So there's the exosphere, thermosphere, mesosphere, stratosphere, and troposphere. And the stratosphere and troposphere are really what we're going to need to understand as far as environmental science. And again, that's what I was kind of saying at the start of this CRAM, is that this unit to me feels very memorize-y, like just kind of memorize these facts without a context of why it's important. So yeah, you don't need to memorize like all of these crazy facts about the atmosphere layers or anything like that. But you do need to understand that the troposphere, so that's the very bottom one, that's where all weather occurs. That's where there's air, which is like, everything that we need to breathe is down there, all greenhouse gases. That's like where all airplanes are. So think of like the highest airplane you've ever seen flying by, like that's still just the troposphere. So that, and it's tiny in comparison to everything else, which is why I like this graphic too, because it kind of helps illustrate that. You can see the little tiny commercial airliner at the bottom is like very close to the bottom, or very close to the surface of Earth. It's not that high. So that's important. So the troposphere is like where we live, and it's where all like air, as we normally refer to it as, is down here, all weather, all clouds. And the greenhouse gases are important. That's what's all in the troposphere. And then the next layer is the stratosphere. And the reason that we would talk about the stratosphere in this class would be because that's where the ozone layer is. And that's important, as far as this class goes as well. So the other ones, like really, as far as like maybe you could talk about how humans have affected it as far as like space trash. We've left some space trash up there, and that, humans have done that, and that affects us because now when we launch rockets into space, we have to make sure that we don't crash into them. But other than that, that's basically just those bottom two. And so again, here, let's talk about like why or how humans have affected those two just briefly to give it context. So the stratosphere, that's important again because of the ozone layer. The release of chlorofluorocarbons caused the unintentional depletion of the natural ozone layer. As a result, increased UVA and UVB rays reach Earth's surface and cause damage to organisms. So the ozone layer is a natural deterrent to UV rays coming in. And when we built these awesome spray cans, so any spray can that has a propellant, meaning any can that you push a button and it comes flying out, that you don't have to like pump your finger to make it come out, that uses the propellant to make it come flying out like that. And typically it was all chlorofluorocarbons until they were internationally banned. But we will get more into that like in Unit 9. But so anytime that you use one of those chemicals were destroying the ozone layer and then causing UV rays to be able to get into, to hit Earth's surface. And if those UV rays hit us as humans, it causes skin cancer and cataracts and sunburns, things like that. It can cause damage like those same things to any animal as well, and it can cause plants like burns on their leaves and damage from those UV rays. It can cause not skin cancer, but it can cause cancers on plants or deformities as well. So that is why, that's kind of how humans have messed up the ozone layer, and then how it has led to damage to us. And then for the troposphere, offsetting the natural current composition of greenhouse gases has caused a dramatic increase in global average temperatures. So greenhouse gases naturally occur in the troposphere. They are very much so good and needed. Without them, it would get really, really, really cold at night, and we would lose all of the heat back into space. So it's important that we have those greenhouse gases. And the only thing is that humans within the last 100 or so years have released a lot more than what were naturally there. And so the thermal retention properties of the atmosphere has increased, allowing it to hold on to more heat on average. And that increase has happened dramatically over, again, those last 100 years. And now we are seeing some of those negative effects of that increasing temperature worldwide as we have increased it. So to not get into those things too much, but to give a little bit of context of like why we're memorizing the layers of the atmosphere, those are the two biggest reasons. All right, so moving right along, let me just double check if we don't have a poll question. I don't think we do on that one, but no, we don't. Okay. Let's keep going here. Let's talk about solar radiation, because we were just kind of talking about that too, and Earth's seasons. Incoming radiation from the sun is the main source of energy on Earth and is distributed unevenly due to seasons and latitude. All right, so we do have a poll on this one. Go ahead and open it up. I'm going to ask it before we get into the content this time. The change in temperature from winter to summer, and those are our pictures there, winter to summer, is caused by the Earth moving farther away from the sun, the angle that solar radiation, I should say, hits the Earth, the speed the Earth is moving, or the distance from the equator. Oh, and I noticed too, some people, we don't always have everyone answering the polls, and sometimes it's kind of hard to see. So right underneath the chat is where the poll appears, and you have to open it. So if you haven't seen that yet, look, open the chat, and then right underneath the chat, you'll see where the poll is. All right, we're getting some good answers. I'm going to go ahead and publish these results. We are torn. Oh, it was almost 50-50, and then we got some more votes right there at the end. The angle that solar radiation hits the Earth is what everyone said is our most voted for answer, and that is correct. The Earth moving farther away from the sun, we don't move farther away from the sun. We are, I mean, not significantly. We're the same distance from the sun all the way around. So it is the angle is the trick there. So that question absolutely might appear on the exam. It is definitely the angle. And let's talk about what does that mean? What angle? So breaking it down, let me get that poll out of the way. Breaking it down a little bit more here on this one. Solar radiation is radiant energy emitted by the sun. And we're particularly talking here about electromagnetic energy. So if you kind of look, these are all different kind of ways here to express or look at the same information that we're talking about. So if you follow that like red squiggly line from left to right, these are the different types of energy coming from the sun, or kind of as we classify it. And it all has to do with like the speed or the intensity of that energy. And so radio would be like the slowest, least intense, and then microwave, infrared, visible, ultraviolet, X-ray, and gamma rays, all coming from the sun, depending on how quickly they move. And then if you look down below those little pictures, and the pictures are there to indicate the like length, the size of the rays. If you're like wondering why there's pictures like little people standing there in butterflies, that's like indicating the size. So you can see like it goes from like a building to being smaller than like an atom. So very, very different, very intense. And then if you go down to frequency, you can see the different lights, like what we can see. So from infrared, visible light is what we can see, and that's like the rainbow. And then ultraviolet is like more intense than that. Not all solar radiation makes it down to Earth's surface, thankfully, because some of it is damaging to our skin, like what we were just talking about with those UV rays. Some are absorbed into the atmosphere, like those UV rays. UV rays come in UVA, B, and C, and like thankfully all of C are pretty much absorbed before they hit Earth, because they would be extremely damaging. UVB are what we are hoping are absorbed in the ozone layer because they are damaging as well. Same with UVA, but again, UVB is like more intense. So that's what we want the ozone layer to absorb for us so we don't get hit by that. And you can't see the UV rays. They're not like in the visible light spectrum to us as humans. So we are going to be hit by them when we're outside, but it's not something that we would be able to see. And then some of that heat or some of that energy is also reflected back out into space. The majority of heat and light are reflected off of Earth. So a lot of that light energy leaves Earth, and then some of that light energy hits Earth, causing Earth to warm up. And so it changes from light energy now to heat energy. Some of that heat energy stays on Earth, thankfully. Those greenhouse gases keep that heat energy in here for us. And some of that energy, remember we talked about, is absorbed by plants. Like a very small amount of that energy is absorbed by plants and turned into energy that humans can use as far as like eating plants and then having energy of our own. And then a lot of that energy is lost as heat back out into space as well. Remember too, when we talk about matter, matter doesn't leave Earth unless we do something silly like eject a Tesla out into space, but it is circling in Earth. That's why you have like the carbon cycle, the nitrogen cycle. It doesn't go anywhere, but energy, on the other hand, is a one-way track. It comes, usually from the sun, and then it dissipates and it leaves the system. So it will be gone. So it comes in and then out and it's gone. It's not cycling. All right, so now that we kind of talked about how that energy is coming from the sun to Earth, this is a diagram explaining the angle of it, which is what was important to us before. Remember, that's what's going to cause seasons. So the solar radiation received at a location on Earth's surface varies seasonally. The tilt of Earth on its axis causes those seasons. So in this picture here, if you notice, is fake. It's false. This is not real life. This is like a simplified version because the equator here is straight across in relation to the sun, and that is not true. So if this was true and this little Earth was spinning around, so again, it's spinning in circles like around itself, and then it's spinning in circles around the sun. As it's spinning around itself, that's a day for us. And then as it spins around the sun, that's a year. If this was true, this picture, we would not have seasons. Everything would be the same all the time. So you could choose like, oh, I like to live where it's roughly 78 degrees out all the time. And you could like move to the point on Earth where it was like that every day. And it would be like really, really cold in some points all the time. It would never become summer. So thankfully, that's not what it's like. This is a more accurate representation of what it looks like. It's tilted. And that tilt, that unevenness, makes it so that we're going to have seasons based on where it is located around the sun. So again, that's a year. So based on where it is around the sun throughout the year. So the Earth's location as it orbits the sun changes, and that would change it from summer to winter as it moves around. So let's say in this picture, that southern hemisphere, the bottom half of the Earth, is going to be experiencing summer because as it spins around every day, it's getting more sun hitting the bottom of the Earth more directly, whereas as it moves around the sun to the other side, it is going to be, oh shoot, and I realize my picture here is the angle is messed up. Shoot, hold on. Let's look at this picture instead. This picture will show it better. So this picture will show how when it moved to that other side, the sun is going to be hitting the Earth more directly in the northern hemisphere. I messed up because I'll show you how. In my diagram I drew, I didn't change the equator. When I flipped my picture, I didn't change the equator to be going the other direction. So sorry about that. I'll change it for the notes. But in the left picture here, the sun is going to be having a more direct angle on the northern hemisphere in that position. So in short, as the Earth moves around the sun, it is going to be receiving a different intensity or amount of light, and that's going to cause those seasons to change. So the angle of the Earth is what causes different seasons. Oops. All right, Earth's geography and climate. Weather and climate are both influenced by solar radiation and geographic features on Earth. So how we kind of just talked about, like in theory, if the Earth's equator was straight across the middle, you could like pick one place you wanted to go. But Earth's climate is also going to be influenced by geography. So like in this picture, you can see some places are very, very green and some places are very brown. And that's because there's a mountain range that is causing like a large amount of rainfall on one side of it and not the other. So it's not just necessarily like the angle of the sun, which is going to dictate what a place is going to be like. It also is then interacting with the Earth, the features of the Earth, like mountains. In addition to mountains, it's interacting with water. So we have to look at, like, again, we're going to bring up that term thermal retention properties. It's a fancy way of saying like different things can hold heat differently. Or better, I guess, than something else. And you experience this every day in your kitchen. If you wanted to get like a hot cup of coffee, you're not going to put it in a glass cup and like grab it with your hand and walk around, because glass exchanges heat very quickly. Same thing with metal. Like you wouldn't get like a thin, no, I'm not talking like an insulated Yeti cup, but like a thin metal cup. You wouldn't put super hot coffee in it and then hold it with your hand because you burn your hand. You're going to get something like a coffee mug that is insulated, and it's going to resist that temperature so that you can hold your hot coffee. If you look at water and land, they have different abilities to transfer heat, and so that manipulates the air around them. The best way to experience this is a very hot summer day. Trying to walk to the pool, you are going to burn your feet. It's going to be super hot, but then you jump in the pool and it's enjoyable, or maybe even cold. And that's because water has a higher thermal retention property. Water doesn't change temperature easily in comparison with rock or like cement. Cement changes temperature very easily. It gets very hot. So if you look at that like on a much wider scale, you're going to see that, let's see what our next image here is. You're going to see that land gets really hot and then really cold, whereas water maintains its temperature. So if you lived in Los Angeles and you were right next to the ocean water there dictates how warm it's going to be, because it's like able to warm the air around it, and it keeps it from having large jumps in temperature. So if you live kind of anywhere around the ocean, you're not going to see like huge jumps in temperature. That's why in Los Angeles, it's usually very mild, very nice temperatures every day. Whereas if you went inland a little bit and you were in the desert where there's not a lot of water, you're going to see drastic temperature changes. So it might get up to 110 during the day, and then it's going to drop down to 50, 40 at night. You know, it might be really cold. So you're going to see very like a large swing in temperatures in areas that are dry. Areas that are humid are going to have much less of a swing in temperature because of that water in the air or the water in the surrounding areas like an ocean or large lakes. Again, just some of our definitions. Weather is a day-to-day change, or it can be like a large event or weather event, but it's still not considered a climate change or climactic event unless it would be 30 plus years. So again, so climate is 30 plus years, and weather is going to be like, oh, it's sunny outside right now. And kind of what we were talking about here. So a rain shadow effect. That's what that picture was at the beginning too. A rain shadow effect is saying as clouds are made over large bodies of water due to evaporation and condensation, then those clouds are usually pushed inland. The reason I say usually, that's look at this picture again here. As that temperature swing happens over land, you're going to have hot air rise, and that's going to cause wind to come in. So if you are around an ocean, you'll notice every evening you're going to have wind coming in from the ocean onto the land. That's going to happen every evening because that land is going to get really, really hot, and it's going to cause the air above it to get really, really hot and rise up. And then you're going to have a void of space where new air is going to need to come in from the ocean. So that's going to constantly be pushing weather in from the ocean. As those clouds hit land, it's going to take a while for them to be able to cross over the top of mountains, and they're going to have to drop a lot of that water in order to do so. Let's go back to our original picture here. That, as you can see in this one, it's going to cause one side of a mountain range to have a lot of green and growth, and the other side is going to be a rain shadow. So it's not going to have any water or very little water. This is famously, again, sorry for all the California references. I guess I'm a little biased here. You're going to see there's going to be a lot of rainfall on the ocean side of all of those mountain ranges. And then on the east side of all of those mountain ranges, it's going to be a desert. It's like Death Valley, large deserts with not a lot of water. And those are large rain shadows. Whew, okay, I wanted to keep going faster because we only got a little bit of time left, and we want to get into El Nino. I know that was something we said we were a little bit nervous about. All right. El Nino and La Nina are a phenomenon associated with changing ocean surfaces, surface temperatures in the Pacific Ocean. Okay, so we're going to try and break this down with some pictures here to explain what is going on. So the Coriolis effect is a force caused by the rotation of the Earth that causes currents in the northern hemisphere to spin clockwise and in the southern hemisphere to spin counterclockwise. And I always remember which way things are going because I studied for a while in Australia, and I remember that they would always call it anti-clockwise, and I thought that was really silly because I had never heard someone call it anti-clockwise. So if you can remember that they say anti-clockwise in Australia, and that down in the southern hemisphere it spins anti-clockwise, then that will help you remember, you know, which one is which. Northern hemisphere is clockwise, and southern hemisphere is anti-clockwise. So as the Earth is moving, it is causing water and air to kind of slosh around or swish around in these spirals. And that is causing like different weather events to happen. So as you can see here, right along the equator, all of the air and water is going to be moving towards the left side of the screen here. And towards the east coast of Australia. And so that equator water, remember we talked about the angle of the rays coming in, the equator is hit most directly, and it's going to have the hot water. So in general here, hot water is getting pushed to the east coast of Australia. And this happens, this is the norm. This is what's going on all of the time. And that's why typically you have very warm water in Australia, and you have the coral reefs, little teeny fish. The water is typically nutrient poor, so that's why you have like small animals living off of coral that love warm water. So that's again the normal. The norm for North America is going to be having cold, nutrient-rich water coming down from like Alaska. You're going to have a lot of upwelling going on as that water on the surface is heading over towards Australia. You're going to have water coming up from the depths that's full of phosphorus and nitrogen, and you're going to have a ton of large fish really good fishing industries, lots of kelp. So again, that's the norm. And by the norm, I'm saying like not an El Nino. This is like non-El Nino, normal times. And then same for South America, you're going to have that warm water being pushed off to the Australia. So you're going to have upwelling of cold water. Those are anchovies. Those are really the basis for a lot of marine food chains. And you're going to have just tons of them. They are filter feeders. So they're, anytime you have like nutrients go in the water, phosphorus and nitrogen, and then you're going to have a bloom of algae, and phytoplankton and zooplankton are going to appear. And those are like microscopic organisms. And sardines and anchovies, then their population just explodes because they filter feed. They swim around with their mouths open and just eat these little tiny things. So they're very low on that food pyramid, and their numbers become just absolutely massive. So again, this is a non-El Nino. This is normal. And then every once in a while, an El Nino event occurs. So that warm water does not go to Australia like it normally does. The winds, again, you're still having the Coriolis effect, so that's not going to go away. But your winds, which are called trade winds, for some reason, they lessen, or they don't completely stop, but they lessen. Enough so that warm water spreads back across the Pacific. So you now have significantly warmer sea surface temperatures in North and South America and kind of across the Pacific than you normally do. And that essentially is what El Nino is. So like the very simplest, the winds lessen. I don't want to say they stop, but the winds are not there as much as they normally are to push that water. And then the hot water kind of sloshes back to the Americas. So in very simplest terms, that is what El Nino event is. Okay, so and then when that happens, this is kind of the results from that. So that phenomena can cause global changes to rainfall, wind, and ocean circulation patterns. North and South America then have a wetter than average conditions and more mild temperatures. So you're not going to have like a really cold winter. You're actually going to kind of have a warm winter. Remember what we just talked about, ocean water dictates temperatures. So that warm ocean water is going to mean that it is now warm on land. These winters typically have a ton of rainfall. So there's going to be a lot of flooding and landslides. There's not going to be a lot of snowpack. So in all of the mountains on the West Coast, both North and South America, they rely on snowpack. So we're talking like, 5-7 feet of packed snow in these really high mountains over the winter that provides water over the summer. So there's not going to be a lot of snow, again, because it's like a wet, warm winter. So there's not going to be a snowpack to provide water throughout that next summer. And then in addition, you're going to have a collapse of fish populations. So in an El Nino year, go back here. In an El Nino year, those anchovies, it's going to be really warm and there's not going to be a lot of nutrients. So those anchovies they can completely collapse. So you'll see like a huge die-off or die-back of that population. And then as a result, they are the basis of a ton of different food chains. And then you also see huge diebacks of those. So frequently in El Nino years, you'll hear in the news about California, Oregon, Washington, noticing a lot of dead baby seals, sea lions, or abandoned baby seals. I remember one year it was just like chaos. Like there was just hundreds of these little baby sea lions, California sea lions, that their mothers had abandoned. And the reason for that is those sea lions eat anchovies. And if those anchovies are not there, either they're dead or those anchovies decided to swim 100 miles out into the ocean, those sea lion mothers can't be tied to the land with their little baby. So it definitely has implications up the food chain as far as harming animals. So definitely sea lions are one that you'll hear about like in an El Nino year. You'll have like a ton of abandoned baby sea lions because there are not the anchovy to support that food chain. Oh man, it's making me click through everything. Okay. And then in Australia and Asian countries, as that rain, they're used to having that warm water. And they're used to having those mild winters with a lot of rain. And as you see that warm water move away, you're going to have severe droughts and fires. And so I know that we all hear in the news about poor Australia suffering really bad fires. And part of that is climate change. And part of that, would be an El Nino year that they would experience that severe drought and fires. Same in like Asian countries, or even in like India, it would impact that way. All right, so in short, that's like the simplest way that El Nino impacts humans and what we've learned about it. It tends to follow a 4-year pattern, but not always. And it tends to follow 4 years, but not always. And I did have a poll question here, but we are kind of out of time. I was going to ask you, like, how do science predict an El Nino year? So I'm just going to tell you this one, by monitoring sea surface temperatures. So we do have like buoys out in the ocean, and you can monitor the temperature. So if you have buoys that are out here in like Hawaii, and you're noticing drastically warmer sea temperatures, then you can predict that maybe we are going to have an El Nino year. You can predict flooding, landslides, and collapse of fisheries in advance. Okay, and last one here. Let me go ahead and open up this final poll. I'm sorry, I got a little distracted here. Actually, my phone just reminded me it's Pi Day 3.14. Oh my goodness. We should all order pizza tonight. Okay, so sorry, this is blocking it a little bit. I will read it for you. So Unit 5 is a beast. There's so many things to cover that there is really no way we can jump into it all in depth in just an hour. So I figured I would open it to you and ask, what should we talk about next time? Should we cover the most important things? Should we cover just like the most important things in each topic? Or should I cover just a few topics like in depth? Do you want me to hit like, what might they ask you on clear cutting? What might they ask you on mining? What might they ask you on pest control? Or do you want me to go like super in depth into irrigation methods, or super in depth into tragedy of the commons? So go ahead and give me a vote on this one real quick here. All right, I'm going to close this poll, but we are unanimous to cover the most important thing in each topic. So I will do that for you. It'll be crazy. We'll have to talk super fast. All right, everybody, thank you so much for joining me today. Again, if you have any questions or want to continue to talk about anything, please join the discussion in Discord. And we will get your questions answered. All right, bye guys. Have a wonderful weekend. Go order pizza tonight.